what I want to concentrate is on sort of why we're going to do this, and some of the challenges, and then sort of show some of the things that have been published recently. So some examples of some of the latest advances. So in the course, we'll sort of cover how we get to some of these outputs, but then also we'll try and talk about some of the sort of more up-to-date applications. Okay, and I know this is kind of, it's a little bit of a joke slide, this one, but you know, why do we want to do reservoir characterization with seismic data? And the idea is to try and get away from this kind of picture. And you know, not that anyone's exploring like this anymore, except maybe some of the shale. You know, you hear some of the stories about shale exploration in the US, where they're drilling lots and lots of wells. I don't think they're quite this close together. But the idea is that we can give information to the geologists and the engineers between the wells without them having to drill a well every 50 meters. And they can't, you know, and the seismic data can give us information in between the wells. Okay, because what we're trying to get out of it at the end of the day is a reservoir model. You know, this is what the engineers and the drillers and the economists want to know. How much, you know, how much porosity is there, how much oil is in there. So the geophysics, the seismic is a tool to give us a better reservoir model. Okay, and there are various sources of information. So geology, waterline data, rock physics, core data if you have cores, and the seismic data, and it all kind of has to be integrated. Okay, so this is something that's, you know, come to the fore relatively recently. So you'll hear quantitative interpretation. I've decided to call the course Seismic Reservoir Characterization, but we could have called it quantitative interpretation. So can I take all these data sets, put them together, and give numbers to the engineers? Okay, and if we've got time at the end, I'll sort of talk about making those numbers sensible in terms of uncertainties. And it's something that we've been pretty bad as an industry, I think, pretty bad at doing uncertainty. Certainly the geophysics and geologists have been. I think the engineers are a little bit ahead of us. Okay, so sort of normal seismic interpretation, we're going to make a map to the top of the reservoir, and we're going to have some idea of the geological setting. We're going to have the faults, we're going to have the structure, and we're probably going to be able to map the thicknesses of at least some of the features, and we can maybe see there are fractures in there, maybe, you know, see compartments. But what we'd like to be able to do is to add something to that. Okay, and this is what we're sort of talking about with reservoir characterization. So can I get an idea of the lithology? So, okay, I've got sand and shale, but, you know, where's the sand, where's the shale in my reservoir? Can I calculate porosities? Can I see porosities? Can I look at saturation? You know, where are the fluids and what are the fluids? And then other things like pressure. Can I tell, you know, what's going on with pressure? And then can I see changes in pressure and saturation? So this is what we're kind of hoping for. Okay, so the sort of blue is the sort of standard seismic interpretation. The red is what we can hopefully add to our interpretation. Okay, and we have some limitations, so it's not perfect. Okay, so our seismic's in this bandwidth in the middle, and there's not really any numbers on there, and that's a little bit deliberate in that, you know, acquisition keeps changing. The bandwidth of the seismic's getting broader, but it's something like, you know, 6 or 8 hertz down here, 80 to 100 hertz up here, and that's the bandwidth that the seismic gives us. And what we find is that to get a good correlation with the geology, we really want to have the full bandwidth. Okay, so we need to have the low frequencies, and we need to have the high, well, and we'd like to have the high frequencies. Okay, and that gives us a better correlation with the wells. So the low frequencies we can get from either the geology or the velocity analysis for the seismic. The middle frequencies we get from the seismic, and then the high frequencies we've got to get from a variogram model from the geology. So if we have plenty of wells, 10 or 20 wells, we can get maybe an accurate variogram. If we only have one well, how good is that going to be? We don't really know. Okay, so we're going to be dependent on our on the bandwidth of the seismic, how good our geological control is, and also how many wells we have, how thick are the reservoirs, so we can get enough data points for our variogram. So this is all going to sort of fit into how good our output's going to be. Okay, so regional geology and stratigraphy is part of this. This is going to be our geological model that so this is a very large scale, but where are the unconformities? What's the big structure? Okay, and that's going to be important. So I'm not going to be looking for salt. There's no salt in there. There's no carbonate in there. Should I have pinch outs? Do I expect to see this sand between these two wells? So that's sort of an important part, and that's going to feed into this low frequency part here. Okay, the well data, a lot of that's going to be from waterline logs. So we need to have some idea of how they work. Okay, and we'll talk a little bit about this a little bit later, but they need to be calibrated because my well logs are in depth in the well, my seismic's in time in general, and so we need to be able to try and correlate them. So we need to have check shots, and this is something that we have to spend quite a lot of time doing to try and match up our well logs with our seismic data. And that's because the seismic data a lot of the time doesn't actually match the well logs. So we have times in the wells from the check shots, and the seismic processing doesn't necessarily match that. So we have to do some kind of corrections. And we can, there are good ways of doing it, and there are more controversial ways of doing it, but we need to match them up. So the kind of logs I'm interested in are sonic, shear sonic density, and then things like gamma ray and caliper logs are useful. And then if I got saturation logs, I got porosity logs. All these things can kind of be brought in there. Okay, but I'm only going to have those data points at the wells, but they're going to fit into this prior model. Okay, if I jump back here, they're going to fit into this prior model. Okay, I might have core data, so that's going to tell me about porosity and things like that. But I'm probably going to have more waterline data than I'm going to have core data. Okay, and what I'm going to hopefully be able to do is have enough well data, or be able to find information in the literature that tells me about the reservoir properties. Okay, so this is a slide that I borrowed from a book on quantitative interpretation by Per and others, and this is showing you the relationship between P wave velocity and porosity for a bunch of different samples here, and you can see they're all kind of there's hopefully you can read the legend a little bit. So different rocks have different properties, and this is going to be something I can use. So if I see in my seismic data something that has a velocity of a sort of 4,000 meters per second, okay, what's that possibly going to be in terms of porosity? Okay, and so this is an important part of taking the seismic data further. Okay, so I'll talk about seismic inversion. We can get elastic properties from the seismic data, but I need to be able to interpret them, and so I need to have some relationship back to the well logs. Okay, so if I increase the porosity, what does that do to my acoustic impedance? So how will that change the reflections in my seismic data? And if I change the saturation, how does that affect my seismic data? Okay, so these are the things I need to have in my rock physics model. Okay, so I've got my seismic rock physics model. I've got some idea of how the seismic should behave. I have my seismic data. And this gives me information between the wells, okay? And I mentioned this already, it's uncalibrated without check shots. The seismic velocities are not necessarily going to match the well, so we have to do some calibration. And I might have different types of seismic data. So I have 2D data, 3D data, time-lapse data. And it's very important that if I'm going to relate my seismic reflection amplitudes to my well logs, that it all kind of matches up in terms of amplitude. And to do that, I need to have what's called true amplitude seismic. And I haven't put a slide in here, but in the course we'll talk about how, what do people do, what kind of processing do we do to make sure that we try and get true amplitude data. Because otherwise what happens is that I can look at my reflections and say, oh, okay, this has got a big, this amplitude and this amplitude look the same, so that's the same kind of change in properties. If my data hasn't been processed properly, then that's not going to be true, okay? And in this case, this is actually a 2D line, and then we have extra problems with 2D lines because we're not quite sure where the reflections are coming from. And so can we be absolutely sure that what we're seeing actually correlates with the geology we think it is? So I have a well at one location, but with 2D data, I'm not even sure if it's actually coming from the same place. But the seismic will give me my framework for my geological model. And then I want to use the amplitudes to try and relate that to properties, okay? Yeah, so what I'm trying to do is identify features of interest, and then see, okay, what do those features match up with? So so here's some seismic data. I think this is data from Australia. You can see there's something that looks like a channel in here, and here's a channel from an aerial photograph from somewhere. Kind of looks like jungle, so maybe South America, and these are the kind of things I'm looking for, and in this channel, I know from the geology where the sand is, or should be, and what I really like to be able to do is to take the seismic data and confirm that in my bars here I've got sand, and I don't have sand other places, or has the channel been filled up with shale, and that's what I want to try and be able to do. Okay, so not just see the shapes, but also try and work out what the properties, what's actually going inside those shapes, inside those features. Okay, and this is where we kind of sort of come into the using things like attributes and quantitative interpretation. Okay, and this is where we also come into amplitude variation with offset and other things like that. So if I'm interested in something like porosity, I could maybe use full stack data, so just normal stack data, and relay that to acoustic impedance. If I'm interested in saturations, I then need to have some kind of shear wave information, and I can get that from ABO. So I need to have the gathers, and so that's a little bit of a limitation for older data sets where maybe the gathers aren't available. Obviously, newer data sets we can acquire the data with a plan to get some wide angles. Okay, and so what we're going to do is try and convert the seismic to elastic properties, and then relate those elastic properties through this rock physics model to things like porosity. Okay, so this is a porosity cube, I think, from the F3 data set in Holland that a lot of you might have seen. It's used in quite a lot of examples. Okay, and this is the kind of thing that the engineers are interested in. Okay, so this is if this is my reservoir interval, where is the high porosity, where's the low porosity? Because then I can plan my wells to follow the high porosities. Okay. We'll talk a little bit about, in the core, talk about a little about the development of time development. So a lot of this stuff we couldn't really do. We didn't really have true amplitude data. we had 3D data, but it wasn't really true amplitude. So a lot of quite a few projects in the 90s didn't work out so well. We have to have pre-stack data, so that limits us. You know, so we couldn't do AVO until the mid 80s because we didn't really have pre-stack data. I think, you know, I've extended this to 2020. The original figure I think stopped in 2010 or even before that. We're now looking at, I think most projects, the data kind of coming out is true amplitude, and we've got results that we can trust. Okay, so that the processing guys know what they're supposed to be doing, and they're doing their best to give us true amplitude. So I can try and trust my outputs. And so quantitative interpretation is something that you know is kind of a buzzword. Okay, but you know, with legacy data, we can't necessarily be sure that we can use that for QI. Okay, and then just to mention depth and time, and you know, I don't know what the percentage of pre-stack depth migrated versus time depth data versus time data is. You know, I'm based in Copenhagen, so it's North Sea, so I think we probably see more of it in the North Sea than you would if you were maybe in other parts of the world. You know, the depth imaging is better. But here's the same data. This is some this free data set, freely available data set from Equinor, Volva. So this is a satellite from Sleipner. And you can see that the depth and time data looks different. Okay, so the depth data is stretched, and the time data isn't. And this causes us all kinds of problems with a lot of the algorithms that we use for seismic reservoir characterization. So some of our attributes don't work very well because basically the one on the left, the depth data, the shape of the wavelet, so the wiggles have changed shape. So some of the things that we do in inversion won't work. So a lot of times what we're still doing is converting our data, is we're taking the depth data and then converting it back to time. So it's pre-stack depth migrated data in time. You know, and that's a little bit unsatisfactory, but I think you can see, you know, you can see the difference. You know, that this looks lower frequency, and so if I try and apply some of the algorithms that we have on this depth data, I'm probably going to get a slightly wrong answer. So right now we're converting our data back to time to do a lot of this processing. Okay. We want to look at the properties of our layers, our reservoir. And one thing we've got to be careful about is tuning. Okay, so you know, it's one of the, I don't know if it's Murphy's law or one of these laws that says that the thing you want is the thing you just can't quite get. You know, so if there's something that's going to go wrong, it's the thing you actually really need is the thing that's going to break. And a lot of our reservoirs that we're looking for, they're getting thinner and thinner. You know, the very big, thick reservoirs have been discovered. And we're looking at thinner and thinner reservoirs, and yeah, we have an issue with resolution. Okay, so my seismic data, as my layer gets thinner, this is, you know, the little wedge model here. As my amplitude, as my layer gets thinner, my amplitude changes, and this is going to change my amplitudes and mess up what you know. Okay, so what's the actual properties here? And this is something I can model, but it means I have a limit. Okay, so lambda over 4 is the sort of maximum of the tuning in theory. I can't see thinner than that. Okay, so if I have 300 hertz seismic, I can see really thin layers. I don't have that unless I'm doing some very, very shallow work. So there is a limitation. So we're not going to be able to really see 1 meter thick layers. Okay, we can try and simulate them or say, well, okay, what would they look like? We can try and do that with stochastic inversion, but we have to be a little bit careful. We're not going to resolve very, very thin layers. Okay, but we can use some of this to try and and pick some information out of our data. So as our layers get thicker or thinner, they're going to tune at different frequencies. And so one of the things we can do is in reservoir characterization is look at spectral amplitude attributes. So we'll talk about that in the course. Okay, so here's the sort of side view of a bunch of these different lobes here, basically. And then they've colored them by what the tuning thickness is going to be. So this is going to be affected by the effectively the tuning thickness. And so depending on the frequency of my seismic, I'm going to get a response. So I'm going to get more from at 30 hertz from the thin one than from the thicker one. And I can use this to try and map out features. Okay, so this is some I think Gulf of Mexico data here, and here's my seismic amplitude. And then what I've done here is I've calculated this CCT is basically maximum amplitude at so if it's all 25 hertz, I get 1. If there's no 25 hertz, I get 0. And so I've done that for 25, 35, and 45 hertz. And then what I've done is I combined them. Okay, so this is a blending, and this is something we'll talk about in the course. And this is the same data set. And I think you can just about see the colors aren't so great. But I think you can see channels and features that show up on this blended image that don't show up on this one. Okay, because what I've done is I've looked at the different spectrums, different spectral attributes, and I combine them to sort of so you can look at them all together. Okay, so if it's only 25 hertz, it'll be red. If it's only 45 hertz, it'll be blue. If it's only 35 hertz, it'll be green. And some kind of combination is lying in between. And I can tune this to look for different features. Okay, so we'll look at that. So this is identifying reservoirs. And here's an example from First Break, some data from Australia. And what they've done here is they've looked, they're looking for these very thin fans here. You can see here's the sort of thicknesses that they're talking about here. And they've identified this area that's kind of blue here. And this is the sort of reservoir or area of interest in here. So you can see there's red parts and then there's blue parts. And they've done this, they've put this little icon in the corner here. And it makes it much easier to interpret everything if you have the little color combination there. Otherwise, it becomes a little bit hard to work out what you're looking at. So the red is where it's tuning at 20 hertz. That's slightly thicker. The blue is going to be tuning at 48, and then the green is 34. So this cyan is a combination of between 48 and 34 hertz. And I can change those frequencies to try and highlight features. So this is one way of one sort of tool for reservoir characterization. Okay, and I can take a bunch of these attributes and combine them. I've got 3 here. I can do that by hand with this RGB blend. If I have 30 attributes, there may be features in there that I can't see, and this is where the machine learning comes in. Okay, so I think I think if you're interested in geophysics, you have to have been I don't know where you have to be, but you can't not have come across machine learning in terms of at least heard of it. And basically what we're doing with machine learning is using so neural nets or self-organizing maps. There are a bunch of different techniques, but basically what it lets you do is, I can look at 3 cubes blended and see something. I can't think in 26-dimensional space, but the computer can. It doesn't have a problem looking at 25 dimensions or 26 or 7 dimensions. And so what it does is it looks for correlations. And so what I can try and do is map out my features of interest by using the neural nets or machine learning to do that. Okay, so here's just an example here. So this is showing a bright spot here. So this is where potentially where the hydrocarbons in here. And this is a paper from another paper from First Break, so Rocky Road. And so this is is it Paradise, I think these guys are working for. And so the different colors here are in the sort of parameter space similar values in all the cubes that have been put in there. And if you look at the paper, you can see they go through all the different attribute cubes that they used, that they've calculated. So the amplitude, the different frequency contents, RMS amplitude, the envelope. So we'll talk about seismic attributes in the course and combining them. Okay. And here's another example. Same paper? Yeah, I think it's the same paper. And this is now sort of a side view. So here's the seismic data. And they haven't shown all the attributes here. But this little map here is this self-organizing SOM map here. So this the different colors, different classifications. And you can see that the AVO anomalies are showing up as different colors. Okay, so where there's an AVO anomaly, it shows up in different colors. And what they've done here is they've just kind of picked out these three, the gray and the red. So these are the AVO anomalies, and the red is kind of the contacts or the flat spots. Okay, and you could probably pick this out yourself on 40 square meters, but imagine, 40 square kilometers. But imagine you've got 1,000 or 10,000 square kilometers that you need to kind of go through. This might actually save you quite a lot of time. Okay, so we'll talk a little bit about machine learning and classification in the course. Okay, my sort of what I've been doing for Schlumberger or did for Schlumberger was inversion. So this is kind of more my my real expertise. So here we're kind of classifying based on attributes. But one of the problems with attributes is that they're based on the seismic data. And that's the layers, the sort of boundaries at the top and the bottom of the layers. And that's not really maybe what we want. What we really would like to be able to do is get layer properties. Because if I have a boundary at the top and a boundary at the bottom, if it's shale, sand, shale, that's okay. Because then the two boundaries are the same but opposite. But a lot of times what's above and what's below isn't the same thing. So the same sand has two responses, okay? And I could maybe unpick that with the neural nets, or work it out myself. But it'd be kind of nice if I can get away from that. And so one way we can do that is to do inversion, okay? And so basically what we're going to do is we're going to use a wavelet, and we're going to basically model the seismic response. So I think you've all seen this if you've done any kind of synthetic modeling for well ties. We do forward modeling. In inversion, what we're going to do is reverse this. So we're going to have our seismic trace, we're going to have a wavelet, and we're going to hopefully get a model out. Okay, we're going to run this sort of backwards. One thing to be careful about is that we're never going to get this picture here on the right here. We're never going to get this out of this because my seismic resolution isn't good enough. Okay, so if I look at this response, I've got what 2, 3, 4, 5 wiggles here. So I can reliably say there's 3 or 4 or 5 layers in there. All this small detail I can't see from the seismic. It may be there, but I don't have any evidence from the seismic. And this is something I need to be very aware of. What's my resolution? So what can I really believe when I'm doing an inversion? Okay, and we can try and make an inversion that's consistent with high frequencies, but we don't necessarily know they're there until we drill a well. Okay, and our inputs for inversion is generally going to be AVO data, and we'll talk about that in the course and a little bit about the theory as well. Where this is coming from, and for a lot of the software, our inputs are angle stacks. Okay, so what we're doing is taking the data, and instead of stacking it all up together, we're going to pick out different angle ranges and produce a whole bunch of different stacks. So 0 to 10, 10 to 20, 20 to 30, 30 to 40. So depending on this angle of reflection down here, angle of incidence, we're going to pick out the data and stack it up. And what we're hoping for is to see some variation with offset. Okay, because that will hopefully tell us about fluids. Okay, so If it's water filled, we don't expect to see very much variation. If it's hydrocarbon filled, we would hopefully see some variation. Okay, and that's what we're trying to pick out, because we really like to be able to get information about VP and VS. Okay, so if I have a rock that's full of water and I replace it with that rock, the same pore space with hydrocarbon, my VP-VS ratio will fall. So what I'm looking for are VP-VS anomalies. So I can maybe get things like porosity from my acoustic impedance, but if I want to have any idea about saturation, what I need to do is use ABO data. So I need to have gathers, I need to have wide enough angles, and then hopefully what I can get out is VPVS. And here's an example from it's Norway, I think. So here's an inversion result, and the red is the well log, the blue is the inversion result. So you can see it's a pretty, yeah, it's an okay tie, not perfect, but it will never be entirely perfect. And this is absolute values here. You can see the dotted line is the background model. So this is our low frequency part. If we just do the relative changes, we don't get a good correlation generally to our well logs. We can try, we can check and see, but a lot of times we don't get a good correlation, and that's because our layers above and layers below, that's the interfaces we're seeing with the relative change. And we need to have that low frequency signal to get a good correlation. But here's the acoustic impedance, and then here's the VPVS, and there's a well location here, and you can see that the VPVS is slightly lower in here. You can see this feature in here, and that's indicating to us that there might be hydrocarbons in there. This is the North Sea. You can see the top of the this is one of these tilted fault blocks, and you can see the erosional surface up here. So here's our reservoir sand here, and it's showing an anomaly in the VPVS. So this is indicating that there's going to be hydrocarbon in there. We have to be careful, okay? So if I kind of go ahead a slide and then I'll come back. So I said that VPVS is important. So I have a low VPVS if I have hydrocarbon. So here's a similar fault block here. And you can see here's my AI, my VPVS here. And I've got lots of low VPVS. So that's all hydrocarbon, isn't it? The red is the low number. But it's not quite that simple, okay? So I have to be a little bit careful. So what I need to do is look at things like depth effects and lithology effects. And so we can try and take that into account. This is one example of how to do that. So again, this is from Per Afseth and colleagues. And what they've done here is they've looked at the depth trend and taken that depth trend out. So here's VPVS versus acoustic impedance on this cross plot. And the depth trend, so this is the relationship between VPVS and AI in the well logs. And then what they've done here is they're coloring it with distance away from the trend. Okay, so basically if it's blue and green, that's not interesting. And if it's red, that's more interesting. So it's a lower VPVS than it should be. And if I then apply this, you can see that all this stuff down here, you can see all the stuff down here no longer looks prospective, okay? Because this is just low VPVS because it's deep, and not because I've got a change in I got a saturation change, okay? It's a depth effect, not a saturation effect. So I've got to be very careful about just looking at one of these plots and going, oh yeah, look at that, that's really interesting. It's a low VPVS, that's where we're going to drill. I need to be a little bit more careful, and that's kind of the thing that we're, so that's the kind of thing we'll try and talk about in this. We'll talk about in this course. Okay. I mentioned that we've got low frequency parts. So we're seeing this. This is our low frequency trend that we need to kind of look at. And a lot of times we have to get that trend from the wells, but there's quite a lot of effort being put into sort of filling that hole. And we'll talk about that as well. And this is one example. So this is using FWI velocities, but instead of running them at sort of 1 or 2 hertz, you see they've gone up to 14 hertz here. Okay, so here's my seismic data. Here's my waveform velocity, full waveform from velocities, and we're using the FWI velocities as our low frequency model. So we're not using the well control. We're going to use the velocities. Okay, so what we can get out is an absolute acoustic impedance output. We can try and fill in the gap also by improving our seismic acquisition. So these new cables that have accelerometers and hydrophones in them. We can do deghosting. We can do FWI. None of it's entirely cheap. FWI is quite expensive computationally. You can see here that it's a little hard to, I think you can't really read the scale, but the vertical scale we're doing, this is quite a shallow prospect here. Okay, so we're not doing it on huge cubes because it's quite costly. But it takes some of the interpretive parts out of this equation. So if I go to build a model, I'm dependent on the well control. If I only have one well, I've got horizons, but that's maybe not going to be a very good model. And something like FWI can help give me a better low frequency model, so I can get my full bandwidth in. We can do inversion for time lapse. Okay, so we'll talk about FWI and building the low frequency models. We'll talk about time lapse. This is again North Sea data. I'm sorry, because it's quite close by. I tend to see mostly North Sea data. And what we have here is a 4D survey, so time lapse. So and I can't remember exactly how much time there is between the two surveys. It's quite a while. But here's my original acoustic impedance and my original Poisson's ratio. So this is a chalk field. So it's actually in the Danish sector of the North Sea, not the Norwegian one that you may have seen. You're used to seeing. I've got high porosity. This is my AI here. I've got Poisson's ratio, which is related to VPVS. So I got changes in that. I got low Poisson's ratio, and this is the change. Okay, and to interpret this change, I need to have a rock physics model. So the rock physics model is very important. For chalk fields, there's a lot of information. If you're somewhere where there's not so much public information, it's a little bit harder. You have to try and produce one yourself. But I can try and interpret, what do these changes in the acoustic impedance and Poisson's ratio mean between my baseline and my monitor. So as I can't remember how many years, but there's quite several years between these two surveys. So how has my reservoir changed? And sort of cutting to the sort of chase with this story was that they found that from the inversion output, the saturation changes were different from the engineering prediction. Okay, so the engineers were predicting one saturation that looked like this. What the geophysicists found was something different. Okay, so we can change the way we're going to produce our field based on the inversion result. So we can update the geological model so that the reservoir simulation fits actually what's going on in the reservoir. You can see this, something happened out here. So the green is the producer, the blue is the injectors. Okay. We can do lithology determination with our inversion results. So this is looking at changes in saturation. We can also try and map out lithologies. So what I need to do that is to basically have a lithology log So in this case, I think they used FMI data. So they identified different lithologies, and then you see there's 3 different colors in here. There's a thick-bedded gas sand, a thin-bedded gas sand, and a shale. And then what I could do is look at the properties again, so P impedance, V PVS here, and work out what the probability of these different lithologies having different values. So these data points are from the wells, and the colors are contours of probability. And I can then use that to convert my inversion results to lithology probabilities or lithology map. So this is some data from Egypt, I think, if I remember. Here's our top of our reservoir here. If we look in a sort of side view, I've got a, which one is it? Yeah, P impedance is the middle one, and then VPVS is the bottom one here. And then this is the prediction of the lithologies at the top. So the different colors are the different lithologies based on this probability here. And then where this is kind of kind of helpful, because I could just go in and look up the values, okay, and then say, well, if it's a certain value and another value, cross plot, make it one color. I can get the probabilities. So I'm doing a Bayesian analysis here, and I can get the probabilities out. So here's a map now, and then here's my Facies, and then I'm getting the probabilities of the different lithologies. Okay, so the thick bed gas sands and the thin bed gas sands probabilities. So what I can do is go in and say, right, everything that's below 0.7 or whatever, I make a decision as to what value is important. I believe in. I'm going to ignore everything that's below that, because if it's 0.2, then it's probably not very likely. It's the most likely, but it's not very likely. Or 0.3. I'm only going to take the ones that have a high probability, and that's better than just having a map and working out what the values are, because then you don't know how much can I trust the data. Okay. We can do joint inversion, and I'll talk a little bit about that in the course. So this is just some examples. And this is from the US. So this is Facies and probability and porosity from simultaneous inversion, so a deterministic inversion. And this is doing a joint inversion. So what they've done is they've done an inversion for properties here, and then they've done an inversion for properties and lithology at the same time. Okay, so instead of getting some output cubes and just saying, right, okay, we'll invert for the properties and then we'll invert for the lithologies, we're going to do everything together. Because if it's a certain lithology, then it's only going to have a certain set of possible properties. And in this case, they get a better tie. We get a better tie to the well logs. Okay, so this is an improvement. Okay, but so I'm inverting for properties and lithology at the same time, because only certain properties are valid because the lithologies limit what the probabilities are. Okay. And then just to sort of finish up, so that you have a chance for some questions, I'm kind of running out of time. Just to talk about stochastic inversion and simulations and realizations and how we can use them. So this is an example from Egypt again, just from a recent leading edge last year. And so in stochastic inversion, what I'm going to do is I'm going to have my angle. I'm going to have my angle stacks. So here are my angle stacks here. I'm going to have my well logs to give me a variogram, to give my properties. I'm going to have a low frequency model. I'm going to have a starting model. And what I'm going to do is produce a whole bunch of models, and they're all going to be consistent with the seismic data. Okay. Okay, so I'm going to have a whole series of these models, and they're all going to be very slightly different. And these are high resolution models. Okay, so these are higher resolution than the seismic resolution. Okay, and they're all consistent. And if I take a mean of 20 or 30 of these realizations, I'll get something that matches my my deterministic, my normal seismic inversion. Okay, so I have a whole bunch of these different simulations. Yeah, so here's sort of zoom in on these different simulations here. So they're all consistent with the seismic data. They're all consistent with the statistics of the well logs. And what I want to do with these is then to try and estimate uncertainty. So this is just showing the comparison with the deterministic versus stochastic. So the two kind of, so the mean of the stochastic should be the same as the deterministic. But what I want to try and do to use these Bayesian outputs is to give an idea of uncertainty. Okay, because when I do my deterministic inversion, I can convert that to porosity from my rock physics model, and that gives me a value for total oil in place or something like that. And it's one number. And I'd like to know what the uncertainty is. So what I can try and do is apply the stochastic inversion here, and my uncertainty is going to come from my well logs. I'm going to add a whole bunch of variations that are all consistent with the seismic, and then I'm going to compare the total. In this case, it's the total sand percentage net to gross here. And so my stochastic, my mean value, my P50, is what I get from my deterministic inversion. But I now get a range of values, and I can use those range of values to actually get some idea of uncertainty. Okay, and that's something that's very useful to the engineers. Okay, so the stochastic inversion is very useful for uncertainty, as is, if we do the inversion here for lithology, I get is it 80%, 94%? What's the, what's the variation? And I can get some idea of uncertainty, because the engineers really want to be able to have some kind of idea of uncertainty in their calculations. Okay, so I know I kind of went through a bunch of stuff there. I wanted to, at least show you some of the things that are out there. The course is going to be online, and we've got 2 dates sort of penciled in here. One in October, so the 12th, so that's in just over a month. So 12th to the 16th of October, and then in the first month of next year, 18th to 22nd of January. So I'll cover some of these stuff, but also the nuts and bolts of getting there, processing the seismic, how we make the angle stacks, we'll talk about, and then also things like how we do well ties. Because it's online, we'll run, I think it's going to be 4 hours per day. And the timing is not, I don't think we've decided on a particular time. I think it would depend a little bit on who signs up. As for the timing, I'm in Copenhagen, which is kind of in the middle. So that would, we haven't put a time of day on here. Okay. But there's I think there's a link to the web page somewhere, so you can see this. But this is the email to register. Okay, but that's sort of all I have. So should I give Shahram? Should I give you the presenter back?
Thank you very much. And
no, I'll hang on to it in case people have any questions. Yeah.
Yes.
Because I can go back.
Thank you so much for your. Yeah, I will first want to thank you very much for the presentation, Dr. Ross, and we will go for a Q&A session. We will have 15 to 20 minutes that the people they can ask their questions.
Yep.
So let me see if I've got any